All right, okay, so no further ado, let's go into some of these substitutions. So I got the first example up here. Whenever you get a combination of sine to a power, cosine to a power, this can be done with substitution. What we'll do is we are going to actually basically look at it this way. Notice I got an even number of sines and odd number of cosines. Well, I'm going to rewrite this as sine squared of x, cosine squared of x, cosine x dx. So there was that extra cosine x, so I decided to split it off. All right. And here's why. It's going to be a u substitution. So I'm going to let u equal just sine x, not sine squared. It's going to be tempting to let u be sine squared, but remember, that's going to require the chain rule to get your du, and you're going to run into issues trying to sub that in. Then our du is just cosine x. So let's talk about the good and where we might have an issue. Oops, excuse me, cosine x dx. Cosine x dx is right here. So our du is a very straightforward substitution, which is why I split off that extra cosine x. U is sine x, so this guy here is just u squared. Now we do end up with this extra cosine squared that we want to substitute somehow. So this is where we go over to our trig sheet. Now this is one that you probably already remember, but check out our Pythagorean identities. Our Pythagorean identities is a relationship between sine squared and cosine squared, right? And in fact, if I take this and solve it for cosine squared, so from our Pythagorean identity, we know that cosine squared x equals 1 minus sine squared x. We now can get this whole thing in terms of u. So u squared, actually, sorry, I don't want to do the substitution just yet, because if you go back to look at this, I want you to see all the steps. Sine squared x, 1 minus sine squared x. That's our Pythagorean identity. Cosine x dx. Now we can get this whole thing in terms of u, because sine squared is just u squared. This here is 1 minus u squared. And this guy is exactly our du. And we've got an integral that's all in terms of u. Like I said at the beginning, I'm going to go through quite a few different examples today, which would be a little different than what we've done in the past instead of just a couple examples. So feel free to ask questions either in chat or if you want to turn on your mic and ask a question. Interrupt me if you need to. If you don't understand a step, let's get it ironed out. Like I said, we may not have time to work in groups today. That's okay. I'd rather make sure you're comfortable with these unique substitutions, with all the different stuff we're going to do today. All right, so now we focus on this integral in terms of u. We're going to distribute the u squared. So we get u squared minus u to the fourth du, that's a 4. This can be done piece by piece. We now have basic antiderivatives, u cubed over 3 minus u to the 5th over 5. It's an indefinite interval, so we'll need a plus c. And as we've discussed before, our last step is to substitute back. So sine cubed x over 3 minus sine to the 5th x over 5 plus c. And there is our antiderivative. Now, one of the things you're going to notice in this section, you probably already noticed it going through the online lesson, some of our antiderivatives are not going to be pretty. Again, remember, I want you to keep in mind what our goal is. We're problem solvers. And the problem we are tasked with is to see how many integrals we can do by hand. We don't care if the final answer is pretty or not. What we care about is whether or not we can find the antiderivative. So this one actually isn't that bad compared to some of the other ones we're going to see. But so I don't want you to get too caught up that the answer looks kind of messy. And in some cases, we'll be able to use identities to clean them up. You know, you don't need to. Our goal is to find the antiderivative. So don't worry. I don't want to worry about making it look pretty. Now we'll do the basic stuff that we always talk about. We'll clean up fractions. We won't leave a fraction in a fraction. If we can cancel some stuff out, we will. But we're going to get some messy looking answers. It's just kind of the nature of the beast, so to speak, on this one. Questions about this first? So this first one, again, this is really just a U sub problem. It just isn't obvious the first time if you haven't seen it before. Well, let's go to the next one. Next example up, cosine squared of x. All right. What we're going to do with this one, we would do very similar if it was sine squared of x. It's a very similar idea. We go to our trig formula sheet. Again, just a reminder, do not think you have to memorize these trig identities. You will have all of these with you. But we want something that takes cosine squared and makes it not squared. We can't just do cosine cubed over 3 because that would, you know, if you take the derivative, you have a chain rule which would introduce an extra sign, which we don't have. If this were cosine squared x sine x dx, it'd be a basic U sub. It's not. If you get a cosine squared by itself, we want to turn it into something that's not squared. So we go to the half angle identities. We're going to look at this guy right here. If you take cosine of its argument squared, it's 1 plus cosine of it, the double its argument over 2. So let's see how that would look. So I'm just going to put this up to the side so when you go to look later, you can see, you can match up with the identities we use. All right, so 1 plus cosine of x over 2. This is going to be nice because now cosine doesn't have a power. This becomes a basic antiderivative. There is one little nuance we have to be careful of. This was for cosine of x over 2 squared. And maybe I should, you know, that's the same as, remember from your notation from trig, cosine squared of x over 2. Those are the same thing. Notice that whatever was in here, this guy got doubled. So x is double x over 2. So over here, since it was x, when we rewrite this, we have 1 plus cosine of 2x all over 2 dx. All right. Whatever was here, if this was a cosine of 5x, this would have been cosine of 10x. And it's just part of the identities. It's just the way it's written, so I don't want it to throw you off. Guys, now we've got a basic antiderivative. I don't want to deal with this 2 in my integral, so I'm going to pull it out. 1/2. 1 plus cosine of 2x dx. I'm going to do the antiderivative piece by piece. 1/2. The antiderivative of 1x, or excuse me, 1 dx is 1. Let's talk about the antiderivative of cosine of 2x. Now, this would fall under our U sub, because we basically have, we got to undo the chain rule here. But I want to give you a way of thinking about it. If you want to do a U sub on this, by all means, do a U sub. There's nothing wrong with that. But let's think about it, because all that's really going on is we have more than just x in the cosine. If we were to do the derivative of this, it'd be negative sine of 2x times 2, or times the derivative of the inside. We're going the opposite direction. The opposite direction means instead of multiplying by 2, we have to divide by 2. So the derivative of, the antiderivative of cosine is sine. Remember, antiderivative is positive sign, derivative is negative sign, of 2x over 2. This gets plus c. Now, let's pause for a second. Where did this 2 come from? Well, again, remember, think about the derivative. If I took the derivative of sine of 2x, well, the derivative of sine is cosine. Leave the inside alone, so that'd be cosine of 2x. Then multiply by the derivative of the inside, which would be times 2. Right? So there would be this 2 in here if we were taking the derivative of this. Well, having this divided by 2 cancels out that multiplying by 2, and that's why we don't see a 2 here. All right. Now again, you can do this. You can do the integral of cosine of 2x dx with a u sub. You know, let u be your 2x, and then du is 2 du, and there's where your where this constant of the 1/2 comes from. All right. Both ways are fine. I just wanted to show you, you know, as you get better at these, this is a shortcut you might use on some problems when all you're really dealing with is an extra constant. Guys, this is the antiderivative. If we want to distribute the 1/2, we can. We could write it as x over 2 plus sine of 2x over 4 plus c. But you were fine here. This is supposed to be a star. Excuse my horrible handwriting. This is the antiderivative. It's 100% correct. If I take the derivative of this, I'm going to get this. Okay. Now, one thing I want to mention, you know, this answer is in terms of 2x because of the substitution we made. If you want to get everything back in terms of x, you can. You just use a double angle identity. I'm not requiring that, but I just want to let you know that you can. So we use this double angle identity right here, that sine of 2x is equal to 2 sine x cosine x. So x over 2 plus 2 sine x cosine x over 4 plus c, and we'll do a little bit of canceling because we can. So if you wanted to not have 2x in your final answer, go to your trig formula sheet and convert it back. Not required. This is a correct antiderivative, but absolutely you can if you want to make it look a little bit more like the original. All right. Okay. Questions at this point? Okay. Yeah, but yeah, if you don't ask questions, you know, I'll assume you guys are doing okay. You know, you can always put a thumbs up if you want to when I check. Let me know that you're doing okay, because like I said, we're going to do a lot of examples today. All right. Now, here's an interesting one. The reason this one is interesting is because sine and cosine have the same, they have different arguments. One is 5x, one is 3x. If they had the same argument, if it was 3x and 3x, it'd be a u sub problem. I mean, no problem. It'd be a very straightforward u sub problem. You could let u be either sine or cosine and go to work. Sine would probably be easier because they don't have to increase negative sign. That's if they had the same argument. It'd be very similar to the first one we did, but even a little bit easier. When they have different arguments, we need to make a transformation. So we go to the trig formula sheet, all right. Notice the product of sum formulas. Notice we have sine and cosine with different arguments, or cosine and cosine with different arguments, or sine and sine with different arguments. So if you see that a product of sine cosine, sine sine, cosine cosine, where the arguments are different, you can use a product of sum formula to make it easier. We're going to use the first one here. So let's see what that transforms this to. It is 1/2. I'm just going to go ahead and straight pull the 1/2 out of the integral. We'll deal with the constant later. Sine of x1 minus x2. So sine of 5x minus 3x, it gets a plus for this particular formula. And then sine of 5x plus 3x. So 1/2. And basically, you don't have to do this. I'm going to do this for this one, for the notes, but I'm going to split this into two integrals. This will be the integral of sine of 2x dx plus the integral of sine of 8x dx. The brackets are because of the 1/2. You could have put the 1/2 in front of both. That's fine too. Just my way of doing things. I like saving the constants till the end. Guys, these are both basic u subs, very similar to the one we did with the cosine of 2x. So the antiderivative of sine is negative cosine of 2x, and we divide by 2 because of chain rule. We're just going the opposite direction. Chain rule, if we were doing the derivative, we'd multiply by 2. So going the opposite direction, we divide by 2. So if we do this one, we're going to have the negative cosine of 8x. What do you think we're going to divide this guy by? So think about if we did a u sub, right? On this particular one, we'd let u equal 8x. Our du would be, oh my gosh, what a terrible 8 that is. Apologies, guys. Our du would be 8 dx. My goodness, having a day today. 8 dx, right? Divide both sides by 8. So we're going to divide by 8. Where does the 8 come from? We'll think about it again. We do the derivative of this. The chain rule would tell us we'd have to multiply by 8. So doing the antiderivative, we divide by 8. Now, and I can't stress this enough, if you're not sure, take your time and do the u sub, okay? It's more important to get the problem right than to do it quickly. But for those of you guys who are ready for this, I wanted you to show the way that I do them, because, if all it is the extra 8, well, then I know that I'm going to, if I were doing derivative, I'd multiply by 8. If I do derivative, antiderivative by double later. Put a plus c on. Again, you can distribute the 1/2 if you want. We don't need a plus a negative. Right? This is negative cosine of 2x over 4 minus cosine of 8x over 16 plus c. Don't have to. Again, this was a correct answer. It is the antiderivative. Okay. Questions on this problem? All right, so dx over x squared plus 4. Basically, any other constant here besides 1. Because if we had this, if it was dx over x squared plus 1, so note, the antiderivative of that is just arctan of x plus c. Okay? So the problem is that we don't have a 1. We can handle that. All right? And it's actually just going to be a little bit of algebraic manipulation. What we're going to do is we're going to basically multiply on top and bottom. Let's actually take those equals out of there. I'm going to multiply the top and the bottom by 1/4, because that's going to get me that 1 where I need a 1. And multiplying by 1/4 over 1/4 does not change what we have. So what does this look like? Well, I've got 1/4 dx. Sorry, it puts that little line in there on the 4s. It drives me nuts. Now here, that 1/4 does have to be distributed to both terms. So I end up with 1/4 x squared plus 1. Okay, because the 1/4 times 1. whatever this number is, you multiply by its reciprocal on top and bottom. That's it. We need that to be a 1. Now, we need to manipulate a couple things to get this to look like an arctan, and I'll show you how we do that. I got that 1/4 there. I'm going to pull this 1/4 out front. So 1/4, the integral, leave the dx on top. This 1/4, I'm going to absorb into the square. All right, what do I mean by that? Well, I'm going to rewrite that as x over 2, the quantity squared plus 1. All right. Now, I want you to think about this for a second. You know, are these the same thing? Let's take a look. X over 2 squared. That's x over 2 times x over 2. You square the x, you square the 2. That's x squared over 4. That, if I wanted to, I could rewrite as 1/4 x squared. So again, I haven't changed what I have. But what I can do now is I can do a u sub. I'm going to let u equal x over 2. And then du is 1/2. Oops. 1/2 dx. Okay. Now, you know, we talked about the way that I like doing substitution. The way I like doing it is I like saying, oh, I need a 1/2 out here, in here, to match up to this 1/2 dx. That means I need a 2 out here. So I didn't change anything. So now I can make my substitution. We can multiply these together. 2 over 4 is 1/2. 1/2 dx is du. And this is u squared plus 1. This is arctan. So I get 1/2 arctan of u plus c. And then I sub that. I let u equal x over 2. 1/2 arctan of x over 2 plus c. And we have our antiderivative. It is not a coincidence that these are both 2's and that they are the square root of 4. Okay? That actually would happen no matter what this number is. Later on in class, when we look at the table of integrals, we'll look this, I'll show you, we'll look this one up, and you can kind of see, oh, if we had done the table of integrals, we could have gone right from the original problem to the end. But I want to talk about the table of integrals a little later. All right. Questions about this one? Again, it's not a straightforward substitution. We had to do a little bit of manipulation first to make it a substitution. Now this guy, because this will lead into partial fraction decomposition, but this is not a partial fraction decomposition for 2 reasons. Number one, x squared plus 4 can't be factored. So even if we wanted to, we couldn't do partial fraction decomposition. But there's something else going on, in this one. And that is anytime you have a rational expression, which is a polynomial over a polynomial, and the numerator, the power is equal to the denominator or higher. You want to do polynomial division to rewrite what you have, okay? So for some of you guys, it might have been a while since you've done polynomial division. We'll do it for this one. You're not going to do a lot of polynomial division in this class, but I want to show it to you. You might get 1 or 2 in the homework. I won't give you a polynomial division one on the exam, maybe the quiz, but it's a technique. Again, it's part of our toolkit. It's another one. It's another integral that we can find the antiderivative of by hand. So with polynomial division, remember the way a fraction works. Basically, this is the same as saying x cubed divided by x squared plus 4. So we're basically taking x cubed and we're dividing it by x squared plus 4. And so basically what you do with polynomial division, you take whatever you need to multiply this term by to get this one to cancel out. So we need it to be x cubed. We're going to multiply by an x. So x, and then it gets multiplied by both terms. We get x cubed, and then x times 4 plus 4x. Normally we'd leave a term here for the squared, but we don't have any squareds here, so we don't have to worry about lining it up. And so what happens is it's kind of like having 0x here. We subtract down. This is the same long division algorithm done with numbers since you were younger. And then we subtract going down. X cubed times x cubed. That term goes away. 0x minus 4x is a negative 4x. Okay. Next you say, okay, is there any whole number or whole multiple of x, integer power of x? Well, we already did x, so the only thing we'll have to do next would be a whole number. But there's no whole number I can multiply x squared by to get negative 4 over x to cancel. Yes, we could multiply by x over, 1 over 4x, but we don't want to do that. We only want to keep this a polynomial. So we've gone as far as we can. This is the remainder. So what we do is we use the remainder theorem to rewrite this. In other words, x cubed over x squared plus 4 is equal to x plus negative 4x over our divisor, x squared plus 4. Okay? That's what's called the remainder theorem. Here's the thing, guys. You've seen this before. If I were to do, let's make it up. Let's say we had a fraction, 5/2. This is 5 divided by 2. How many times does 2 go into 5 without going over? It goes in twice. We have a remainder of 1, and we're dividing by 2. So as a mixed number, 5/2 is 2.5. This is the same thing, guys. It's pretty cool, right? You know, we've been doing it with numbers for years. We can do the exact same algorithms with polynomials. It's really cool. So this what this polynomial division does is now we go and we rewrite our integral as x, and if you want, we can pull the minus out and write it as 4x over x squared plus 4 dx. We're going to do this integral piece by piece. So I'm going to do an x dx, which is a nice easy one, minus, excuse me, I'm going to pull the 4 out because it's a constant, x over x squared plus 4 dx. Guys, this is a u-sub. This is one of our fairly basic u-subs. So let's do this guy. X squared over 2. Nice and easy. Actually, not. This one, our u, we're going to let be x squared plus 4. And then our du is 2x dx. Sorry for getting a little messy here. And don't worry, when it comes to the exams, the problems are chosen, specifically to not be too cumbersome algebraically and not be too long. That's what the take-home problems are for. That's what the quizzes are for. So we need a 2 in here because of the 2x dx, which means I need a 1/2 out here. Just squeeze it in there. And so minus 2 times the integral. The 2x dx is du. X squared plus 4 is our u. So we have x squared over 2 minus 2 ln. Remember that I do want you to get in the habit, ln of the absolute value of u. plus c. It's an indefinite integral. Clear as day, we can see we've got a contradiction in our variables, so we don't want to miss subbing back. Here's our u. Kind of plug it in for that guy. Well, that wasn't helpful. Let's get rid of that. Plug back in our x squared plus 4. So x squared over 2 minus 2 ln. You don't need the absolute value because x squared plus 4 is always positive because of the plus in the square. So if you don't want to write it, you don't have to. If you put it in, it does not make it wrong. Okay, so when in doubt, include it. And there's our antiderivative. So what I want you to take from this one, when your numerator has a higher power than the denominator, you start with polynomial division. You use the remainder theorem, which is this guy here. That allows you to rewrite your integrand. Typically, this part will be easy. It'll be some basic polynomial, real easy antiderivative. What's here is going to depend on what the original function is. This may be a u sub, maybe a trig sub, which we're about to see, maybe a partial fraction decomposition. But it does allow us to do one like this by hand. Okay. Questions about this one? All right. As you can see from our worksheet, we're getting into partial fraction decomposition next. I probably won't do all of these all the way through. I'll do maybe the first one, maybe the second one all the way through. The other ones we're just going to set up and maybe go a little bit. I just want to show you some stuff, some nuances. And then, if we have time today, I'll let you guys work on them. But if not, I'll send you the link to the solutions to all of these. And it's also in more. I'll show you where it is. Same thing's going to go with trig substitution. We're going to do the first one all the way through. After that, we're just going to talk about setting them up because we will start to run out of time later. And there's some very important nuances I want to show you. And that's why we've got the variety of examples. But I've got the solutions ready to go for you guys. So don't worry. Okay. Partial fraction decomposition. What is it? When do we use it? Partial fraction decomposition is actually an algebraic technique. What it does is it splits to fractions. Okay. Basically, if we had 1/2 and we want to split that into 2 fractions, we could look at things I want. Shoot. Sorry, not the best example. Oops, too far. So when we add fractions, let's do it that way. When we say, okay, we're going to do 1/2 plus 1/3, we find a common denominator. So there'd be 6. So we'd have 3/6 plus 2/6. This would be 5/6. Partial fraction decomposition says, okay, how do we split 5/6 into something that's more manageable? So we go this direction. We're splitting 5/6 into 2 separate fractions. So the goal of partial fraction decomposition is to split this into more manageable integrals. Now, the way you're going to recognize partial fraction decomposition is you are going to have a rational expression in your integrand. The numerator will have a smaller power than the denominator. If not, you do polynomial division. And your denominator will be factorable. If it is not factorable, partial fraction decomposition won't work. Okay, so this needs to be able to be factored. So first thing you do is you factor your denominator. And this is going to factor into x minus 3 times x plus 1. Okay. We're going to do some factoring with 9, 10, and 11. I'm not going to spend a lot of time on factoring, guys. If you need practice on the factoring, make sure you get it, because there will be some factoring, not just in this section. It will come up every once in a while in the class, but obviously for partial fraction decomposition, there will be some factoring. If your denominator can factor, you want to. That's when you're, we talked about this last class. We wanted to have a way of saying when we want to use which technique. If you get a factorable denominator, partial fraction decomposition is a definite candidate. All right. So what you do next is you want to rewrite this in terms into fractions. One of them with a denominator x minus 3, one of them with a denominator of x plus 1. But we can't put the 1 on top because we don't know that it's 1. We don't know what the numerators of these separate fractions are going to be. So we represent those with a variable or variables. And what we typically do, what's the convention, and that you saw in the online lesson, we use capital letters. We start with A and work our way through the alphabet. So what is that going to look like? I have A over x minus 3 plus B times x plus 1 dx. So this is where the method of partial fractions gets interesting. Our goal now becomes to find A and B, and then do our integrand from there, our integral from there. How do we do that? Okay, I'm going to take a little bit of time on this on the first one. We won't take as much time on it on the next one because I'm going to show you how I like to think about it, how it's a little bit shorter. What we need to do is first off think about going the opposite direction. Okay, what would we do if we needed to add these two fractions? We would find a common denominator, right? We would make this A times x plus 1 over x minus 3 times x plus 1 plus B times x minus 3 over x plus 1 times x minus 3. Okay, this is back to your algebra days. Find a common denominator. Now we can add the fraction. And we want this to be equal to 1 over x plus 3 times x plus 1. Now, one thing I want you to notice, the denominators are already the same. So what you're going to see when I do the future examples, I won't include the denominators. I'll just include the numerators. All right. So what we get is 1 equals A times x plus 1 plus B times x minus 3. I am going to show you a couple different ways to solve this. This is going to be a system of equations. I'm going to show you 2 different ways to solve this one. I'm going to show you a very nice, easy way that won't always work based off of what you have. I'm going to show you a little bit longer way that will always work. All right. So let's talk about the shortcut. The shortcut, let's do it in what color have we used? How about green? If I can find a good green here. Man, where's the regular green? Okay, that's it. Longer than I'd like. Okay, so one quick method, when all your denominators are linear and you don't have any repeated ones, there's a very nice quick thing you can do to solve your system. What you would do is you zero out one of them. So for instance, you let x equal -1 because that will zero this out. So what that would give us is 1 equals A times 0 plus B times -4. That's, of course, 0, which is why this is so nice. Divide by -4, we get B equals -1/4. Okay. The way I picked -1, I wanted to make this 0. So for this one, I'm going to pick x equals 3. And I get 1 equals A times 4 plus B times 0. And this, guys, this is work. This is mathematically sound. There's nothing wrong with this. It just isn't general enough to handle all of our cases. When we have repeated roots, which is going to start happening in some of these other examples, this won't work. All right. But there's going to be, you're going to do ones in the homework that this works perfectly for, and I want you to have it as part of your toolkit. So there's our A and our B. We're going to plug those back in here in a minute, but I want to show you another way of solving it. Okay. Let's go back to blue. Let's talk about what's going on here. I have 1 equals, I'm going to distribute AX plus A plus BX minus 3B. All right, that came from distributing the A and distributing the, all right, that's all well. Now, the way I'm doing it now is the way I'm going to do the rest of the examples. So, again, I want you to have access to this method, but this is the one that I'm going to use. So you'll get a lot of practice with this one, or you get a lot of examples of this one. Here's where the system of equations comes in. And I have a particular way I like to write it or organize it, and I'll explain it. So I like to do it in powers of x. We have an x to the first, which is representing this x, and an x to the 0, which is representing the constants, because we could think of this as a times x to the 0, because anything to the 0 power is 1. Okay? Now, this one, you're probably like, well, why didn't you just write 1 and x? Well, when we get more of these, you'll see, but this is my way of organizing. Because you're going to see that I don't write the x's on the right-hand side. So what I'm going to do is I'm going to take every term with an x. So I've got a times x, so that's an a, plus b times x, so plus b. So that takes care of this term and this term. And notice over here, I have no x's. So a plus b equals 0. Then we do the constants. I have a minus 3b. These are the constants. Let's put that in there just for note's sake, constants. And there is a constant on this side, and it's 1, so that has to equal 1. Yes, we have a 2-by-2 system of equations. This can be solved with substitution, elimination. For time's sake, I'm just going to do a real quick elimination on it. I subtract going down. A minus A is 0. B minus a negative 3B is 4B. 0 minus 1 is negative 1. Divide by 4. I get B equals negative 1/4. All right, boom. And A plus B has to equal 0. So what does A have to be based off of that? Well, it's got to be the opposite of B. If adding those two together equals 0, and there's our 1/4. All right. Now, once we solve that system, we're not done. We have to go back and we have to plug those in. I'm going to go back to purple because now we're back to this. Let's bring this all the way down here. Not the best, maybe not the best bookkeeping. Sometimes I like to do this off to the side. So I might do that on the next one. This one got a little messy. I'm still getting used to writing on some of these problems on these whiteboards, especially some of the longer problems. So apologize for the messiness. You plug in the A and the B. So we have 1/4 over x minus 3 plus a negative 1/4 over x plus 1 dx. I'm going to pull those out and write these as separate integrals. So 1/4. Oops, yeah. Let's write it this way: 1 over x minus 3 dx minus 1/4 of 1 over x plus 1 dx. Guys, these are both basic U subs. Because of time's sake, I don't have time to go through it all because there's still so much I want to go through with you guys. But these are going to end up being natural logs. We end up with 1/4 ln absolute value of x minus 3 minus 1/4 ln of the absolute value of x plus 1 plus c. We could play around with this with properties of logs, but I don't want to use class time up for that right now because, like I said, we still have 7 more examples that I want to talk to you about. We're not going to get all the way through them, but I want to show you the nuances and all. Okay, so here's what I want you to take from this one. You do the factoring. That's the denominator factors. That's your note that there's partial fraction decomposition. You set up your partial fraction decomposition, which then allows you to set up your system. You solve your system, plug those back in, and then you integrate. All right. So we need to go on to the next one. Won't have time for too many questions on this one, or any questions on this one, because I want to make sure we get through a couple more of these. There's stuff I want to show you. So let's go to the next one. I'm going to try and do this one a little neater too. All right. We check. Denominator is smaller than the numerator. Power. Denominator factors. X squared plus 1 over x squared times x minus 1 dx. When this happens, when you have this is what's called a repeated root, because x is repeated twice. When you have a repeated root, you have to account for it in your setup. What do I mean by that? Well, let's take a look. You have to do all the possible iterations of the repeated root, meaning I have to do, okay, a over x. I also have to do b over x squared, because both of these are possibilities, and I need the variables for my system. And then finally, I get c over x minus 1. Again, this is what's called a repeated root. If this had been x cubed, we would have done a over x plus b over x squared plus c over x cubed plus d over x minus 1. All right, so on and so forth. If this had been a to the 5th, we would have done a over x, b over x squared, all the way up to e over x to the 5th. That's how you handle a repeated root. It's needed for your system. Excuse me. Okay, let's talk about setting up our system. Like I said, I'm going to show you the way that I like to do it. It's a little quicker than what we did in the last one. So each of these guys has to be multiplied by what it needs to make the common denominator. Here's the common denominator right here. That's our common denominator. So what does a need to be multiplied by? It needs to be multiplied by another x and x minus 1. Okay, I'm doing the same thing we did last time. I'm just doing it in a more condensed fashion. B needs to be multiplied. Well, that's our common denominator. It already has the x squared. It needs to be multiplied by x minus 1. And then C already has the x minus 1. It needs to be multiplied by the x squared. This needs to be equal to our original numerator, x squared plus 1. So all I'm doing is what we did last time. I'm just not writing the denominators. Okay? Then the next thing we'll do is multiply everything out. So we'll distribute the ax. So ax squared minus ax plus bx minus b plus cx squared equals x squared plus 1. Now we set up our system, and we have an x squared term, an x term, and a constant term. So next, we're going to set up an equation for the x squareds, the x's, and the constants. X squared terms, we have a plus c equals, and we have an x squared over here, right? That means it's going to be equal to 1. I'm writing the x squared out here instead of writing ax squared plus cx squared equals x squared. That's all that this is really. It's a way of organizing it. X to the first. I've got a minus a plus b No x's over there, so that equals 0. X to the 0, I've got minus b. That equals 1. And there is our system. We actually already know that right here, b equals -1. Okay, if b is -1, and we plug it into this guy, we end up with -a minus 1 equals 0. So that gives us a equals -1, because we need -1 to be positive. Again, time's sake, I've got to start going a little bit quicker to get through all this stuff. I apologize for that, but I want you, there's so much stuff I want you to see today, and that to me is very important. And now that we know a is -1, this becomes -1 plus c equals 1. Add the 1 over. C equals 2. And then we plug in. Oh, shoot, I want to change back. But again, guys, I will take questions. If you have questions as I'm going along, please ask. That's important to me as well. But I am going to start going a little bit quicker on some of the stuff that's kind of repeating. Plus -1 over x squared plus c, which is 2 over x minus 1 dx. Now you do this one piece by piece. Here's one thing that I see happen, and I want you to be careful of it. Because a lot of these partial fraction ones, they do end up being natural logs. Don't get in the habit of making 1 over everything a natural log. What do I mean by that? This is going to be a natural log. This is going to be a natural log, but this one is not. This is a power rule, okay? So take your time on that. Make sure, if you're not comfortable with these yet, use substitution. Use your antiderivative rules. Okay, I'm not going to finish that one because I want to go on to the next one, because something interesting and different happens in the next one, which is an irreducible quadratic. What does that mean? Okay, we factor the denominator, x squared times x squared plus 1 dx. This guy is an irreducible quadratic. I cannot factor it any further, but it has a quadratic. So notice what I have. I've got a repeated root here and an irreducible quadratic. So let's talk about what that looks like when we when we go about setting up our system. We know how to handle a repeated root. When it's linear, it's just a over x plus b over x squared. We handle all the iterations up to whatever max power this is. When you have x squared plus 1, an irreducible quadratic, you have to account for the fact that the numerator might be linear. So what does that look like? Cx plus d. All right. Once again, 2 reasons for it. The numerator might be linear, plus we're going to need the c and the d for all of our equations. We have to have as many variables as equations to solve our system. So that's why we're going to need 4 variables in here. And this is only with an irreducible quadratic, meaning you factored as much as you could, but one of your factors is a quadratic that cannot be factored any further. We're not going to do it in here, but if you had an irreducible cubic, then you would make this numerator a quadratic. So all this stuff just builds. Again, we're not going to do that. Do not worry. Now then, we'll get through this. All right. Well, most of that stuff was good. So a was times x squared plus 1. B was times x squared plus 1. Here, this should have been cx plus d is being multiplied by x squared. This is going to give us a much more interesting system. Is equal to x minus 2. Ax cubed, because a should not come out to 0. Ax. I was going to get an error in my system. My system was going to be inconsistent. That's how I noticed it. bx squared plus b. And then this one, cx cubed. Come on. Plus dx squared, and that is equal to the x minus 2. All right. Again, back to setting up our system. X cubed, x squared, x to the first, and x to the 0. So x cubed, again, now here's where the difference comes. A plus c, there's still 0 x cubed on this side, so that doesn't change. The x squareds are going to be b plus d equals, again, 0. There's no x squared terms. The x is going to be a. And let's double check. That is our only x term. So we do know what a is, and it's going to be 1 because we do have an x term over here. And then finally, our constant term is just b, which equals 2. So this is not a hard system. You can back solve it. But let's see. Yeah, I'm going to leave this one here because of time's sake. Because I do want to get to trig substitution, and one more thing I want to show you with these systems. Recording gets posted after class every time. Okay, guys, I'm going to do this one a little bit quickly because there's a point I want to get to so that we got some time for trig sub. And don't worry, like I said, I have solutions for all of these problems, and I'll be sending those out. All right, so first thing we do is we factor. So we got 2x squared plus 5. This is going to be a factoring by grouping. Again, if you need some practice with factoring, make sure you get it. I don't have time to go over that right now. X squared times x minus 1 minus x minus 1 dx. Basically, I'm pulling a negative out of these two terms, and I pulled an x squared out of those two terms. Notice I've got a common factor of x minus 1. So I got 2x squared plus 5 over x minus 1. And what's left? X squared minus, when we factor that out, there's still a space holder, minus 1. Now, because this is a minus, this is still factorable. This is plus, this would be an irreducible quadratic. It's still factorable. We're going to still go one more level. 2x squared plus 5 over x minus 1. This is difference of squares. It factors into x minus 1, x plus 1. So we don't have an irreducible quadratic, but we do have a repeated factor. So when all's said and done, we have 2x squared plus 5 over x minus 1 squared, x plus 1 dx. So when we do this, we've got a over x minus 1. Let's include the parentheses to make it messier. X minus 1 plus b over x minus 1 squared plus c over x plus 1. All linear. This is a repeated linear, which is why it does not get the bx plus c. All right, this is what's going to build our system. So just like I've been doing before, let's change the color for consistency. All right, a needs to be multiplied by, well, this is our common denominator. It needs an x minus 1 and it needs an x plus 1. B, it already has the x minus 1 squared, which is great. It just needs the x plus 1. And C needs the x minus 1, the quantity squared. And this needs to be equal to the original numerator. 2x squared plus 5. Okay. I'm going to go through this. I'm going to do the algebra on this a little bit quicker than I normally would for time's sake. This is just, there's a lot going on in this section, guys. Apologize, I know I'm throwing a lot at you, but there's so many nuances that I just want you to see. This is x squared minus 1. We'll multiply that out. So that's ax squared minus a plus bx plus b. And this has to be FOILed. This is, x squared minus 2x plus 1. And then we distribute the c. So plus cx squared minus 2cx plus c. All right, we make our system. This is going to be a 3 by 3, squared, x to the first, x to the 0. X squared, what do we got? We got a plus c. That's it. And that equals 2. So that took care of the x squareds. The x's, we have b plus c. There are no x's, so that equals 0. And then we have our constants. We have negative a plus b plus c, and that has to equal 5. We need to solve this system. I want to show you how to do a system with your graphing calculator. All right. So what we do is I'm going to line these up so that they look a little bit cleaner. So I have 1a plus 0b plus 1c equals 2. I have 0a's plus 1b plus 1c equals 0. And I have minus 1a plus 1b plus 1c equals 5. We're going to use the calculator in a matrix to solve this one. There's a video of this in the, this is done also in the lesson, I believe, but I want to show you from the TI-84. This is the same as the TI-83. You do second matrix. We want to edit the matrix. If you want to use the first one, that's fine. Enter. Now what we have is it's rows by columns. We have a 4 by 3. So 4, excuse me, we have a 3 by 4. Got that backwards. A 3 by 4. And all I enter in the matrix is the coefficients. So 1, 0, 1, 2. All right. So see where those came from. 1, 0, 1, 2. 0, 1. This is actually really cool for you guys. A lot of you guys are going to take linear algebra. You guys are going to do this stuff. So I'm kind of showing you how to do it with the calculator. Minus 1, 1. Because you're going to get some messy systems in the homework. I have no problem with using the calculator on this stuff. All right, everything's entered into the matrix. And here's what you do. You quit out of here. You go back into second matrix. This time we're going to do math on it. You're going to scroll down to RREF. It stands for row reduced echelon form. We're going to hit enter. Then I'm going to put in that matrix. The second matrix. I'm putting in A. And then enter. There are my answers. This guy, because it's in the first column, remember first column was A, second column was B, third column was C. That's my solutions. A equals -5, B equals -7, C equals 7. We'll plug those back in, and then we'll do our antiderivative piece by piece. Okay. All right. We got to get a trig sub, 1 or 2 trig subs in here. So sorry to not have time for questions right now, but we need to get a trig sub. We've only got about 17 minutes left. All right. Next one. Let's talk about how we identify it as a trig sub first. If you see something like this, a squared minus x squared, a squared plus x squared, so on and so forth, these are on the sheet. If you see anything of these three forms, these are the substitutions you use. So this one we're going to do completely. The other ones, if we have, whatever time we have, we're going to talk about, right? So we look here, we say, oh, under the radical, I've got 9 minus x squared. Which one does that look like? Well, it looks like the first one. And so I use x equals a sine theta. This is a forward substitution. It's a little different than the u substitution. So the first thing you do is you say, okay, then a is the square root of this number. So we're going to let x equals 3 sine of theta. That's the first thing you do is you get your substitution in. The second thing you do is you find your dx. It is the derivative of whatever you have here. So it's 3 cosine theta d theta. Again, this is a forward substitution. I don't have to make anything fit. I actually literally just plug things in. So my x is going to go in for the x's. So I have 3 sine of theta cubed square root of 9 minus 3 sine of theta squared. And here's the part that most people forget. This is the most common error on trig sub, is forgetting to sub in the dx, which is a 3 cosine of theta d theta. We're going to do this one completely because there's something I absolutely got to show you at the end. The other ones we won't. Okay, what do we do next? Well, we're going to take care of these constants because they're going to get a little messy. And here's how I do them. I don't worry about multiplying them out. I've got a 3 cubed here and another 3 here. That's 3 to the 4th sine of theta. So let's talk about what's going on under the radical. 9. This is 9 sine squared theta. And I already took care of this 3. Okay, it was combined with 3 cubed, but I still have the cosine theta d theta. Now what I'm going to do is I'm going to factor out the 9. So I have 3 to the 4th sine of theta. This is going to be why we do the trig sub, times 1 minus sine squared theta cosine theta d theta. Well, this is this is one of our all of this is based off our Pythagorean identities. 1 minus sine squared is cosine squared. So what happens next? If you want, you can take the 9 out of the square root, make it a 3. We're going to be doing that anyway, so we'll do that next. Usually I'd write the 3 to the 4th, but I haven't done it yet, so we'll do it in the next step. This is going to be square root of 9 cosine squared theta. So let's note, we're using a Pythagorean identity. One minus sine squared theta equals, gee. Sorry, guys. It's right, and my hand's cramping up a little. Cosine squared theta. That's our sub there. Cosine theta. Notice what that's going to do. It's going to get rid of the square roots. This is a perfect square. So we end up with 3 to the 4th sine of theta, 3 cosine theta d theta. All right, let's get these 3's out of here. Let's put that 3 with this 3. That gives us 3 to the 5th. I'm going to pull them out this time. Oh, shoot. This, guys, I got to go back and fix something. This sign should have been, because it was cubed up there. A sign's got to be cubed. Apologies. sine cubed theta, and cosine times cosine is cosine squared theta d theta. That's basically why we do trigonometric substitution, is to get rid of things like this radical. Now, this should look kind of familiar. It's very similar to the one we did earlier. The only difference is we're going to let u be cosine instead of sine, because sine is what we have extra of. So now, not only do we do a trig sub, we've got to do a u sub. So u equals cosine theta. We did one like this earlier, so I'm going to go a little quicker on this part. Negative sine theta d theta. So that is going to introduce a negative. Right, I need a negative in here, so I'm going to put a negative out here. You just have to be aware of that. All right, now our substitution is very similar to last time. Remember, we're also going to use the fact that 1 minus sine squared is equal to cosine squared. Well, actually, technically, we're going to be saying the fact that sine squared theta is equal to 1 minus cosine squared theta. Because we're going to be doing that on this guy here. The extra sign, we use it for our trig sub. So we have minus 3 to the 5th. This is going to be 1 minus cosine squared theta. Skip that step. It's going to be cosine squared theta. And then here at the end, we've got the negative sine theta d theta. Now we can get this in terms of negative 3 to the 5th. We have 1 minus u squared times u squared, and that is exactly our du. We'll distribute the u squared like we did before. Minus 3 to the 5th. U squared minus u to the 4th. du. And kind of like before, minus 3 to the 5th. Fix that. Times, now we're going to have in parentheses u cubed over 3 minus u to the 5th over 5. And whoa. Plus c. All right. We are far from done. We have done 2 rounds of substitution to get this in this form. So we are going to have to fix some things. I'm going to need some space. So let's get rid of this. All right. Now it is time to sub back. Okay, so let's sub back, and let's just for organization, I'm going to change colors on this because this is the one thing I want you to see about. There's something I want you to see about subbing back with trig sub. The first one is pretty straightforward. It's the same subbing back you do with your u sub. U is cosine of theta. We need to get that in there. So negative 3 to the 5th. We got cosine of theta. For right now, I'm just going to write it this way. You'll see why here in a second. You don't have to. You can put 3 there. It won't change what we got. Over 3 minus cosine of theta to the 5th over 5 plus c. All right. Now, we have to sub back again. Our original was not in terms of theta, it was in terms of x. So we have to use this to sub back. We need to get cosine of theta in terms of x. You have 2 options, and I'll show them both to you. Number 1, if you solve this, we know that, let's do it here. X equals, we know this. So we also know then that sine theta equals x over 3. To find cosine, you can either use the Pythagorean identity or you can use a right triangle. So if I were to use a right triangle, here's how this works out. So there's my right angle. I call this guy theta. Sine is opposite over hypotenuse. Pythagorean theorem tells me this is going to be the square root of 9 minus x squared. This should look familiar. Look at what we started with. So that tells me that then cosine of theta, which is adjacent over hypotenuse, is rad 9 minus x squared over 3. If we had done Pythagorean theorem, we know that cosine squared theta equals 1 minus sine squared theta. So we plug that in. We have cosine squared theta equals 1 minus x over 3 squared, or 1 minus x squared over 9. Finding a common denominator would give us 9 minus x squared over 9. And then taking the square root of both sides is what gives us cosine of theta equals square root of 9 minus x squared, and then the square root of 9 is 3. You got user preference on that. Whatever you think is easier, you'll see in my videos I like using the right triangle. It's going to be a mess, guys, but this right here has to be subbed in for the cosine up here. So we got to be a little careful. So minus 3 to the 5th. We have square root of 9 minus x squared over 3. Remember that though gets cubed over 3. Let's put a big old bracket here. All right. Minus, same basic thing, square root of 9 minus x squared over 3 to the 5th over 5. Bracket. I'm going to clean this up a little bit, so bear with me on this. Minus 3 to the 5th. We don't like leaving fractions in fractions. So what is this going to look like? Well, this is going to be 9 minus x squared, the square root of it cubed. So that's going to be to the 3 halves. Square root is the same thing as raising to the 1/2. Cubing it is to the 3rd power. Multiply those together, you get to the 3 halves. This is going to be a 3 to the 3rd divided by another 3 is 3 to the 4th. Minus, right here, same basic thing, right? 9 minus x squared, except it'll be to the 5 halves over 3 to the 5th times 5 plus c. And if we distribute this negative 3 to the 5th, well, we have 4 3's here, and we're going to have 5 of them on top. That's going to cancel down to a minus 3 times 9 minus x squared to the 3 halves. Here, all 5 of these are going to cancel out with all 5 of these. The negative is going to switch the sign, and we're going to have 9 minus x squared to the 5 halves over 5 plus c. It is not pretty. If you have to use trig substitution, a lot of times the answer does not come out pretty, but it is another integral that we can do by hand. Guys, we only have 2 minutes left, so I'm not going to get to the other examples, but I will send you the solutions, and I'll show you where they are right now in course materials. So this is in course content, course materials sorry, no. If we go back into the course, excuse me, go back into course content, we're in module 1. I keep all the worksheets at the beginning of the module. Here's 5.5, the worksheet I sent out. Here's the solutions. All right. And along with videos for the solutions. All right. So you'll have all the solutions for these ones. Let me, so you have the link as well and put it into the chat. I'll send it in an email too. There's some really good examples, and like I said, we didn't get to 13, 14, and 15. There's interesting things going on in each of these. 13 is a secant, and it shows you how to deal with a 16 being out in front of the x squared. 14 involves completing the square to get it in the right form, and then 15 is a tangent for the substitution and a definite integral to show you how to deal with that with trig sub. All right.